Thanks, Ben, for the introduction. So this is my first Tapestry, and also my first semester as an assistant professor, as well as my first time talking to an audience that is largely outside academia. So hope you survive me. So talking about my research, over the past few years, I have collaborated a lot with experts, and I strongly believe in the value of working with real people, real data, and their real problems. So talking about domain experts, they are serious people. So starting with some serious quote here. So it says, "I know what I'm doing. Please, no more GUI. If people need a GUI, they aren't qualified to be doing whatever they're trying to do." So this was about a study that was published in Kai about 12 years back. And obviously, this person here is not in favor of using a GUI as opposed to a command line interface. A less angry quote, but equally skeptical, is by a climate scientist who I have collaborated with, who opined that changing a color map will only be a cosmetic change, and it won't lead to any practical benefits. So the context of my talk will be focusing, in the course of my talk, I will be focusing on these class of visualizations that are designed by scientists and are found in publications or reports, primarily to communicate their findings to people within their community or outside their community. Right, so what these two quotes show you is the effect of familiarity. People in specific domains are familiar with either their own data, the domain-specific practices, or the tools that are used. Familiarity is a good thing because even in real life, when we make decisions, when we deal with people, many of our decisions are based on familiarity, right? And even in HCI, it has been shown that human-human relationships are replicated in human-machine relationships. Familiarity leads to preference, confidence, and comfort levels. But I'll say that familiarity also has some hidden consequences. It's a precursor to certain kinds of biases that get manifested in bad design. And I'll give you some examples of bad design. The examples that I will show you are all taken from publications, primarily in climate science and biology. So let's start with some spaghetti. So this is a very popular plot actually used in climate science to convey temporal variation. And in this case, if you don't know what you're looking for, it's very hard to untangle this spaghetti. So it's a very apt name. This is what I call a data superstore because the analogy I would draw would be with when you're going to grocery store, when you exactly know what to find. In this case, the design actually expects you to exactly know what you're looking for. And I would contend that a table is actually a bit better than this design where there's different kinds of shapes, there are too many variables, etc. There are also examples which we find in these domains where certain kinds of plots are convention. So this is called a Taylor plot, used to convey agreement or disagreement among climate models with observation data. This was designed by Carl Taylor, I believe, back in 2002, and it's very, very popular. So the way you understand this plot is look at any specific point. It conveys three different statistics: standard deviation, root mean square difference on the x-axis, and correlation on the right. So the closer this red point is to where it says reference, the better a model is. But every time I see this plot, I have to actually remind myself how to read this. And the problem becomes when there is a combination of models, which are here, they're indicated by these different symbols, and also the numbers which indicate different variables. So it actually relates to a general problem with, say, scatter plots when we are trying to represent many different categories for each specific point. Okay, so the next one is obvious, right? So it's our favorite bashing boy in the visualization community, the rainbow color map. It's a serial offender, but it is still the most popular color map that is used in the climate science domain, right? So I've given you these examples, right? So of bad design. So what are their causes? So one of the causes is that scientists not only design their own visualizations, but they actually generate their own data. right? And so in my experience, I haven't seen a more faithful data lover than domain scientists working in, say, climate or biology, where they generate their data with, say, perform large-scale simulations. And what happens when they design visualizations is they don't want to get rid of that data. And this is a popular problem, which is referred to as loss aversion. This was a term coined by Tversky and Kahneman, which says that you are trying to minimize some kind of loss, in this case data loss, as opposed to gaining something out of it, right? So in this case, there is very little attention paid to the message that is being communicated through these charts, but the main goal is to minimize the loss of data, which is a problem. The other factor is the examples that I showed you, like spaghetti plot and Taylor plot. They are conventions in the climate science domain, so people prefer using these all over and over, rather than looking at other viable alternatives. In some cases, people just don't care, and there is also a general lack of awareness about what value, say, a different color map would give to climate scientists. So I have faced this quote over and over again by my collaborators, that which goes back to the quote I showed you, where changing color would only, they would only perceive it as a change that is related to aesthetics and not the functionality of the chart. So we have these causes which lead to these poor design choices. So what are the consequences? We can obviously understand the consequences if we compare these bad design, examples of bad design, with examples of good design. Which means before understanding consequences, we need to come up with better alternatives. Let me give you some examples of alternatives. So a good alternative to a spaghetti plot would be a solution like this on the right, where there are small multiples of line plots, where each line now belongs to its own panel, which is a model. There is this black line, which indicates the mean of the population, and this gray shading, which indicates the standard deviation. So now you don't need to bother about untangling this one particular line from a sea of lines, but you can readily understand, readily compare across these different panels, and also within each panel you can compare with the mean and the standard deviation. This plot was actually really appreciated by my collaborators, and they started using this as an alternative to the spaghetti plot. Second is an alternative to the Taylor plot. So in the Taylor plot, again, what you're trying to do essentially with respect to different metrics, statistical metrics, is to know how well models agree with each other. So if we can come up with an alternative representation like on the right, which I call a slope plot, where each line is a model and each on the x-axis are the different output variables, then you can follow the paths of these lines and compare the different slopes, and also readily know which are those output variables, which is very difficult to know from a Taylor plot when multiple symbols are used. And you can understand, for example, if you compare the blue and the orange models, you can see that they disagree a lot across the correlation and root mean square error metrics, which are two statistical metrics that quantify model performance. Even this plot was really liked by some of my collaborators, and we used this in a study, and I'll show you later. The alternative to rainbow is rather obvious. So we can use different multi-hue or single-hue color maps that preserve the perceptual properties. And even here we conducted a study, and I'll show you the results. So first, the study that we did comparing the number of visualizations that were ranked according to levels of familiarity within the climate science domain. So mainly I will show you the comparison between the Taylor plot and the slope plot. First, we had 3 different tasks. All the tasks were based on comparing these, as you can see from the slope plot, they're comparing across different models and output variables. So in none of the tasks, the Taylor plot, they were more accurate with the Taylor plot. Actually, on one of the tasks, the slope plot was statistically we found a statistically significant difference in accuracy using the slope plot as opposed to Taylor plot. So we can say from this evidence that familiarity was definitely not a driver for performance accuracy. But again, from the HCI literature, we know that familiarity drives subjective preference. So what about that? What we did was we asked people to rank the different visualizations based on familiarity, pre-study. So on the x-axis, you see the percentage of people who assign different ranks. So in here, I'm showing you the ranks 1 and 2 mainly. I will comment on the ranks 1 and 2. So if you look at Taylor plot and slope plot, you can see that about 25% people ranked it as number 1 for familiar, as the most familiar visualization, and close to about 12% for slope plots, but that percentage changes drastically when we ask them to record their preference levels, rank their levels of preference post-study. So close to 50% of the people said that they preferred slope plot the most, which is kind of contrary to the literature that we're aware of, that familiarity is a strong driver for subjective preference. So this was a good result, and we are currently encouraged by the effectiveness of the slope plots and building an actual tool incorporating that within the visualizations that climate scientists would use for model comparison. The second study was comparing color maps with the other perceptually effective alternatives. So even in that case, we could replicate the result that we found earlier, that the rainbow color map, in none of the tasks, the rainbow color map, they were more accurate with the rainbow color maps, but in one of the tasks, they were significantly less accurate than other single hue or multi-hue color maps. However, when we looked at their preference levels, we found that familiarity in this case was actually a driver for subjective preferences, because most of the people indicated a greater level of perceived accuracy, confidence, and preference levels for the rainbow color map. On the other hand, they were significantly less accurate, at least on one of the tasks with rainbow color map. And I will be presenting this paper in InfoVis next year. This is just published in TVCG. So what do these results mean for the big picture? So we have data that gets transformed to visualizations and gets communicated. The examples that I showed you are the visualizations that are used for communicating to within the scientific community. So there is an opportunity cost in visualization design that scientists face, because there is a lack of effective tools that would work within their environment, mainly their scripting environment, that would guide them to use viable alternatives. So many of the tools they use have bad defaults, and there is a significant amount of work they need to do to overcome those barriers. On the consequence side, we have made some progress on showing that the familiar alternatives might not work as well as people think they work. But there is a lot of work to do if we expand the scope of the visualizations that we study to the ones that are used not only in scientific publications, but in reports such as in climate science. The IPCC report is very popular for communicating insights to a broader audience like the public or the policymaker. In that case, I will say that perception, we have made a lot of progress on perception-based design principles, kind of the known unknowns, testing on the known unknowns, but there are also a lot of unknown unknowns on the graphical interpretation side. How do people actually read data and connect them to higher level concepts, especially when they are trying to learn something, a scientific concept? How does engagement or persuasion work with visualizations? And I see some of that work is beginning to be done in the visualization community, but even more work needs to be done, and that's why I think a community like this is really great, and I look forward to the interactions with you all. I would end by acknowledging the contributions of my collaborators and some of the great scientists who I worked with, none of them who were like the angry system administrator, and who always were open-minded and accepted some of the design problems that exist in the community and were open enough to incorporate the new features as part of their workflow. With that, I would like to end my talk. Thank you.